So to start off this project, want to identify one of our main objectives, which is to be able our main objective for our robot. And it's to be able to avoid obstacles. Reach a beacon within an arena, so that it simulates like a Martian environment. And so some things that we immediately noticed with this challenge and those objectives was some potential problems that maybe any robot, including ours, might face, like internal heating, reduced mobility because of how unpredictable the terrain can be, and limited expertise, like ourselves, on robotics and quality design tests and those kind of things. But we also know that like different types of robots and the mobility design of those, and like their pros and cons and what we had to weigh in. So from those, we then have designed and got our robot together. So we'd like to introduce the RTST, which stands for the Rough Terrain Sensory Terraformer, which is able to move in all directions and avoid obstacles like rocks, sticks, branches, and such. It's compass navigated and is able to maneuver the terrain completely autonomously. So some things to know is that it is based on a tank design, so that it can have the most absolute maximum traction when maneuvering the terrain. And so that's mainly the main part of the challenge. Though, like everything that is built, there are some needs. So the tank design for the RTST is certainly will need high torque motors and a large reliable power source for those high torque. High torque requires high power. And the power supply could something like a lithium ion or a standard DC battery. It does need some pretty high clearance since it is a tank, and since we are trying to get through some of those obstacles and some of those environments and those arenas. It certainly will need like 3 to 4 inches of clearance below its treads or between its treads. So we most definitely did a design where we'd have our tank tread systems on a separate chassis that links upwards to the actual piece of the tank. And also, because we are using a tank, we want to include a special individual suspension system, which allows the tank to maintain its grip on the ground without it bouncing around so often. And because we are also limited on the budget in this challenge, we decided to make the majority of the RTST to be, like 3D printed. And the main reason we did that, or one of the reasons, is that it's light, it's durable, and it has a really low cost, which is one of like the really good features of 3D printing. Besides the electrical components, the chassis and all the other mechanical parts will be 3D printed, which is pretty much the majority of our design overview. In our documents, we included all of our thought processes and designs with making our bot and the designs for it.
Hello, my name is Cesar Ibarra. I am one of our team's coders. My job was to give life to our robot and to give it the ability to reach a beacon, or in other words, go from point A to point B. And our objective was to essentially give life to this robot to reach its mission. And by doing that, we decided to break down our robot's essential components into small objectives. So our very first step was to learn how to program an Arduino chip. So we decided to learn how to program the Arduino chip to turn on an LED. And an LED is a light emitting diode. It's a small light bulb. And an Arduino chip is a small, compact, cheap, programmable chip that is available to anybody. Doing the LED project, that led us to program more difficult and bigger components. So our next step after that was to program the way our robot was going to be able to see. We were given the option to use one of two components, an infrared sensor or an ultrasonic sensor. And we decided to use an ultrasonic sensor because I personally have had experience of programming one in the past. We were able to detect proximity, or how close an object was. At first we weren't successful with that, so we found some sample code online and we borrowed it and we modified it enough to make it print readings on the Arduino serial monitor. and we had those readings converted to centimeters. So we were able to see, or the robot was able to see, how close an object or an obstacle was in centimeters. And so the programming of the robot's eyes then led us to programming an Arduino with an Ardumoto shield. An Ardumoto shield is essentially an electrical overload shield for the Arduino. It mounts on top of the Arduino chip. It was hard to program because we needed to learn what PWM was in order to program the Arduino with the Ardumoto shield. After learning what that was, we acquired some sample code from SparkFun. This was used to begin to program the Ardumoto shield with the Arduino, and it wasn't successful at first because the Arduino wasn't able to withstand much electrical load that we wanted. Essentially, we discarded the idea and we moved on. The Monster Moto Shield was the other option that we had, and it does the same thing as the Ardumoto Shield, but the Monster Moto Shield is a bigger, more robust electrical shield for our robot. With this new component, we were able to move forward in our project, and so with the sample code that we acquired for this Monster Moto Shield, we were also able to program the motions for our robot. So we connected two electrical motors onto it because we decided to use two motors. And with the code and the Monster Moto Shield with the Arduino, we had the ability to move the robot forward, backwards, and we had the option to stop. The sample code that we acquired was designed more for human input. It wasn't the robot making its own decisions. So by inputting either 0, 1, or 2 in the serial monitor, 0 is stop, 1 is go, 2 is reverse. And we later on wanted to modify that code so that the ultrasonic sensor were to work together with the Arduino in order for the Arduino to make its own decisions to either move forwards, backwards, or to stop. But due to unfortunate events, we were not able to do that. That was going to be our next step in the project. But we did manage to get the robot moving, through user input, and to be able to detect proximity of objects with the ultrasonic sensor. So what powered essentially our robot was a huge battery. I believe it was a 7-volt battery. I'm looking at it right now. It was a 7.4 exactly. 7.4 volts exactly. It's a big battery. We had to find a secure way to hook up this battery to the Monster Moto Shield because we essentially used jumper cables, and that wasn't very safe because they weren't secure. The wires were exposed. So we were given some terminals. It was a male and female terminals that we soldered onto wires and onto the original terminal of the battery. So that was a much more safer way of hooking up the battery. It also allowed us to, in case of a fire or if something were to fail or started smoking, we were able to unplug the battery right away. That was one of our biggest safety concerns for this robot. And everything else, all the major components before, for our prototype robot, they were hooked up on a breadboard. And on this breadboard, they were hooked up with jumper cables as well. So this was how we were going to run our prototype. And in short, with all the code's functions and everything hooked up together so far for our prototype, our robot, through human input, it was able to move forward and backwards constantly and to stop as well. And the sample code also allowed us to change the wheel speed as well through human input. It wasn't the robot making its own decisions yet. And all of this combined as well with the ability to detect proximity with the ultrasonic sensor. So this is what we were able to do. It wasn't much. So yes, thank you.
Hello, my name is Kai Marsick. I am actually our team's leader. So essentially, I'm going to be going over the final topics for our robot here. So we're going to go ahead and start with our overall design and layout. Each aspect of the tank is specifically designed just to work as efficiently as possible. So we've gone through for each aspect of our tank and designed it to the best that we could think of just together as a team. However, we did end up, settling with a certain design. As I'll put up a picture here that you're able to see. Just the process of going through each and every one of them is what we had fun with, honestly, and just working as a team to make sure that each aspect is designed specifically. We did the best that we could with the time that we had. So the chassis is intended to be lower profile, as Kelly mentioned. Obviously, we're making it out of 3D printed material, which is highly lightweight, and but it can be durable at the same time. So it's really good for us to be able to have that lightweight material as well as cheap material to build our robot that we're able to handle to a certain extent. We all think that would have been the best route to go, is to have that 3D printed final design. So essentially, as for the motors, so the motors are actually mounted on the front of the chassis. There aren't any rear motors or any motors in the middle, anything else. We just have the front wheels are mounted to the motors. That should provide with the best traction as well as keeping the weight down, just giving us a good amount of torque so we don't have to worry about connecting more motors in the back to the ones in the front. So it would have been a little bit easier just to have those front two motors. All of the wheels, other than the ones that are mounted to the motors, have a bearing inserted into it. The bearing is what is mounted onto the chassis, which the bearing is mounted onto the wheel that holds the treads in. And that would have provided the least amount of resistance from the treads, because having those wheels just running off of a axle or something like that would have had more resistance on the treads. And so having those bearings to put on the wheels would give us the least amount of resistance, so we could have more torque and essentially more power. The bearings or the wheels, none of that is really any concern to the weight. It's all pretty lightweight, especially since the wheels and the tread is all 3D printed. Speaking of the tread pieces, we went over plenty of designs of that. We ended up finding a good design that we went with that actually works pretty well. We had started printing pieces out for experimental design and testing, and it was going well. Killy was actually taking care of that. He was sanding the pieces down, making sure that they all fit, and just doing basic testing on it. And it actually went pretty well. Basically, the concept is that the wheels all have a gear-like kind of style. So the wheels have the divots that go inside, and then the tread actually has the prongs that will go into the wheel. So as the wheel rotates, it hooks onto the prongs of the tread, and it pulls it along the wheel as it rotates. And then the rest of the wheels also have the same kind of style so that they can stay on the track. Otherwise, the track would just slide and fall off of them. So they all have that same style of like tread, little pieces that are sticking out to go into the wheels. So those are, just some basic examples of how detailed we got into designing the robot. Caesar has done a good job on testing all the coding for the electronic components that we're going to be using, so that we were prepared for when our process got a little bit further. I was trying to help him with coding the motors and figuring out just the fine details in the code so that we could work out the best course of action, just according to where we were at with the coding, because that's pretty much the most important part. Without the coding, we wouldn't have a functioning bot. And, as well as laying out the electronic components That's another big part, because if we have, unequal balance or something like that, it's going to throw the whole robot off. And just having that equilibrium and etc., just right placement of the components is super important. So when it comes to timeline and budget, our timeline was, initially projected just to keep us on schedule and as productive as possible. Before the unexpected complications that came up, we were right on schedule and we were moving along quite well. We were testing and really getting detailed into the different aspects of it, and it was going well. Nonetheless, our coding began, and design was working out well, and that's pretty much where we ended up stopping. Was just we weren't able to print out the chassis, and we didn't get any of our components, but we were able to mess with some coding and some testing components that we were provided through the classroom. Um, and so we were moving along quite well. Um, and Furthermore, everyone in the group has done a great job in their part. So with Killy and myself working on the design, and Caesar and Mohammed working on the coding and electronic layouts, it's gone quite well, and we worked well together, and we were on track. We were following our schedule quite well. Not being able to finish our robot is a little bit disappointing, because we were all looking forward to it, and we were moving along well and having a good time and learning a lot. But nonetheless, I think just this opportunity was good for all of us to learn and to work as a team. And as far as we got, we did wonderful. Um, and it just illustrates how passionate we all are for, being able to have this experience, and having the opportunity to be uh, pursuing this field, pursuing the engineering field. Thank you for watching our presentation. I hope you enjoyed our layout of our robot design. If you have any questions, feel free to contact me, or any of our group members. We are the A9 Industries. That's the name of our group. Other than that, we'll see you later.